And thanks everybody for coming. I'm really excited that people came, period. So that's awesome. I'm Bradford Stephens. I'm the CEO and founder of Drawn to Scale, and we make an easy-to-use distributed database with a full text search and a rich query language. And I was asked by Ed and the folks at O'Reilly to come talk a little bit about building scalable systems. Now this talk, we're going to do a little more breadth than we are depth. So jump between a few major topics. So if you have questions, feel free to ask them in the chat room, preface them with Q, or write them down on a pad so you don't forget, because I'm going to be jumping through a lot of topics here. But hopefully there'll be a little bit of something in here for everybody. Let's see now, how do I... Is the second slide showing up for everybody? Okay, great. So I've got an interesting background, or I think it's interesting anyway. Spent some time in politics as a campaign manager, spent some time in music, but I ultimately have a computer science degree from the University of North Florida. And there I studied machine learning and distributed systems. So, there's a few major topics we're going to go over today, a few major areas that this information is in. Sort of the biggest one that comes to mind is operations, or how you handle your clusters when they're live, or the systems you're building when they're live, how you deploy them, things like that. Also engineering, down to the actual code you write, what that code looks like, a little higher level than that, but really the nuts and bolts of building these systems and some tips for making it easier on yourself. And finally, businesses and processes. A lot of times we neglect the fact that building large systems or building things in the cloud can be a change from the, even at people who don't write code, at the actual business itself, all the way up to the CTO, CEO level. So just a few quick anecdotes and stories on how to handle this big data world from an actual business perspective. So something important to remember is that really when you have big data and when you're building these distributed systems, it really changes a lot of aspects of how you build it. The bar is set a lot higher. In the web world for years, if you had Linux, Apache, MySQL, and PHP, you could build pretty much everything. I mean, this powered MySpace. This still, I think, powers Facebook. It's a very standard stack and a way to process your data. But you don't really have that in this big data world. Everything has to be cobbled together by hand, whether you're using Hadoop or HBase or Cassandra or building your own key value store for some reason. Because you're having to cobble together these things, you really need to have top-notch engineering, because a lot of times when things go wrong in these systems, you won't find out for hours later, or you won't know until you get these odd cascading failures. So you really have to look at how you build stuff from the ground up in order to even achieve minimum success, or you're going to be in a lot of trouble. So, how did we get here, and why does big data matter, and why does scalability matter? 5 or 6 years ago, things were really different. You had a few large databases at whatever companies you were at. They might have paid a few $1 million to Oracle for them, or they might have had a few large data warehouses, and that's really it. But now with this new web scale world, everything is interconnected. Whether you're accessing a Twitter API and then doing a mashup against your sales results and perhaps feeding in Facebook comments, everything is connected to everything else. And you can write web crawlers, you can access APIs. It's so easy to get large amounts of data these days. And it's really hard to figure out what you need and what you don't need. So you tend to save all this data, which is why things like Hadoop are so powerful. Some of the uses of Hadoop are some of the most mundane things you've ever seen, like storing log files. The storing log files turns out to be really important. Even a few years ago, we would have just thrown those away because there were too many of them, or we didn't think we can get intelligence from them. And the size of data you have isn't really related to how big your business is anymore. It used to be that, the Fortune 100 had the 100 largest databases. But now you've got little startups like Flightcaster who crunch through 7 or 8 terabytes every few hours. And they're about 3 people because all this data is so easy to get to these days. So, when it comes to thinking about scalability and how you store your data, the traditional database has brought us really far, but it gives us a lot of problems. And it's one of the reasons why I'm having this talk today, is because these problems have led to this massive field of research and all these new practices that are springing up to get around the limitations of traditional architectures. So traditional databases are really great with structured and normalizable data, things you can do join against or extract structured entities from. But the problem is twice as much data in a database may cost you 4 times as much. Twice as much again may cost you 8 times as much in terms of hardware, people to handle it, and so on. Pretty soon, just to add more storage to your database, you can pay millions of dollars in hardware, license costs, things like that. So if you want your business to grow with your data, traditional databases, it can be really difficult to do that. Not always, but often. And of course, the more data you add to a database, the less features of it you can use. Pretty soon you can't have joins anymore, you can't do indexing, you can't do full text search. So you don't really get most of the benefits of SQL, which is a pity because SQL can be really useful. And traditional databases are really built for single nodes. When you shard out MySQL or try to make MySQL distributed, you lose the advantages of secondary indexes, of joins, and things like that, which is one of the reasons why my startup Drawn to Scale built the Spire platform to get around the limitations of traditional databases not built to be distributed. Lots of other people have had to build their own platforms as well. And you may notice, with a traditional database, almost all the utility is from very few functions: grouping by, sorting, sums, counts, filters. When you look at pretty much any page on the internet, it's hard to think of more than 5 or 6 different SQL operations they use to build it. And so, since traditional data infrastructures are very difficult to make scale linearly or very difficult to spend more money on to gain capacity in a linear way, we have to build web architectures that are distributed. So that means you really have to optimize these architectures for their problems because, Swiss Army knives don't really exist anymore. You could traditionally do anything with your old style database, slicing and dicing data, storing it, searching it. But these days you'll often see clusters optimized for batch processing, for key value storage, or for low latency serving of images. Everything you build has to be optimized for the problems it's solving, or otherwise you're going to fail at all your objectives. A lot of times too, Google really pioneered this infrastructure, but you'll be building these things on commodity boxes. And by commodity, I don't mean $500, I mean $2,500, 16 gig of RAM, 8 core, 24 gig of RAM, stuff like that. And these infrastructures are often going to be shared nothing, meaning very rarely is there a single point of failure. Even Hadoop doesn't have a single point of failure these days. Things like that. And you'll want it to scale linearly. If you have twice as much hardware, you would expect it to be twice as fast or handle twice as much data. So, the things have really changed from where we've come 20 years ago when it comes to building large systems. The most important thing is the customer experience and everything it takes to enable your web pages to be fast or those queries to be fast. 20 years ago, we were waiting for robots to pull things out of tape decks, and if you had 80 by 60 screens of green text, that was a fine customer experience. And another extremely rare resource besides your customers is engineers. It's far easier to buy $50,000 of hardware or $200,000 of hardware to find one engineer worth $200,000 that can build these kinds of systems. So you have to really maintain the scope of what you're building, or you're not going to be able to find the people to even build it. I/O is really expensive too. Disks have not become faster over the years like processors and RAM has. So you will need to have a lot of boxes often with hundreds of gigabytes to terabytes of memory across your entire cluster, instead of having just a lot of large, fast disks, because they'll fail often or you can't build the infrastructure to handle that. So in order to enable these good customer experiences, you have to have I/O systems that are fast. And that often means serving things from cache. Excuse me. But at least the good news is one of these variables, storage, is really cheap. You can buy, just the other day I bought 1.5 terabytes of storage in an external drive for like $80. Remember 10 years ago, I thought the world would be a magical place when I could store a terabyte of my Ozzy Osbourne MP3s. So that kind of brings me to one of the big major features of this whole talk, which is about recovery-oriented computing. And this should really be at the core of your thoughts when you're building systems that have to handle large amounts of users or large amounts of data. Things need to be seamlessly partitioned, and this is a huge pain point that everybody from Twitter to Facebook or anybody doing like sharded MySQL has discovered, is that dividing your data among these machines is a very difficult thing. And if your algorithms aren't right, or if your failover stuff isn't quite right, you're going to run into a lot of problems trying to figure out how you get your data split across these machines and query them so that there's no hotspots and things like that. Everything needs to be synchronously redundant, and Hadoop is a pretty good example of this. But if you yank a computer, your users should know. Things should fail over elegantly and without intervention. And you're right, guy with dogs. That's a really good question that I should address up front. When I say large amounts of data, I basically mean more data than you can use on one computer quickly. And so that may mean different things to different folks. You may not be able to serve queries out of a 250 gigabyte database quickly, or you may be able to do 10 terabytes of data on one machine pretty quickly. But when I talk about big data, or when I talk about things like that, what I basically mean is more data or more users than can handle, than one machine can handle. And just to address Tim's question, although I'm usually not going to answer questions during this, our Spire database, you can find more information at our website, drawntoscale.com. But you can check that out after the presentation. It'll still be there. So the third big aspect of recovery-oriented computing is that it needs to be really heavily monitored, because you can't hire enough ops guys to log into your machines to check on them all the time. So just as important as the data infrastructure is the ops infrastructure around it, and finding these DevOps guys who can write code and do operations and monitor these large clusters. So this kind of brings me to the first point, the first large of our three sections of this talk, which is operations. You want to move the box to sysadmin ratio from 2 boxes per sysadmin to hundreds or thousands. Because if you're building large clusters, you just can't hire and coordinate the amount of people you need to manage them. And developers, this will be part of your life too. You'll notice pretty quickly that if you are developing, large systems, that you'll be working really closely with the operations guys, because, whether it's bugs in your code or bugs in deployment, mistakes have much larger impacts. So it's a funny story I was kind of told, or not maybe a story, just an anecdote about operations versus engineering. Engineers tend to build things, and operations tend to manage things. So what that means is when problems come up, developers are going to code and automate the problem away, and operations guys, because they usually don't develop code in these systems, they'll hire people to mitigate problems. They'll hire folks to restart servers or to write scripts to make deployments. This is really important, because if you're not prepared to run a 50-node cluster or even a 20-node cluster, when things go wrong, if the engineers aren't hearing about it, or if not put in your Scrum backlog, if you're using Agile development, then pretty soon you're going to be hiring more and more ops guys to do really mundane things like restarting your services or moving data from one machine to another. So if you really want something fixed, don't give just the ops guys calls, have the devs get called at 2 a.m. They'll discover really quickly what the major pain points are, and not only management will advocate to get these problems fixed, but the developers will want to fix the problems so they can sleep through the night. So definitely call your devs when things are going wrong. Don't leave it just to the ops guys. Another really important thing when it comes to preventing those 2 a.m. phone calls is understanding that configuration is incredibly important in these systems. It's not a second-class citizen anymore. I've run sites who get millions of hits with nothing more than apt get install MySQL, install your LAMP stack. I never even had to configure anything. But with these systems, because you've got so many pieces you have to bring together, configuration can be a very difficult problem. A lot of times, I rarely do consulting these days, but a lot of times when I was called in to do consulting in organizations, I asked them, how's your Hadoop cluster doing, or how's your Cassandra cluster doing? And they're like, well, it took us 5 months. It took us 5 months to understand how to configure the thing. And some of this is a problem with the open source world in general, where documentation isn't as good as it should be. But a lot of times you'll have ops guys trying to configure garbage collection parameters, and that's something that really needs to be handled by engineers. Engineers have to both set up the systems and actually build code on top of them. There's things out there, we use Chef a lot internally with our Spire database, but there's things out there like Chef or Puppet that bring together development and operations to make these deployments easy. But Chef has come a long way, but it still can be kind of a pain to get started with. And they've got a really great community there at OpsCode. But you have to dedicate resources for engineering these problems, when before you could basically just install the thing, click a few buttons, and it would just go forth and conquer. Configuration should be on your backlog and is just as important as rolling out new features. Another thing you're going to realize really quickly is that if you have more than 10 or 20 machines in production, you don't really have a test environment anymore. And this is really strange. Things like test and staging don't really mean the same things they do when you're building these big systems. Because what's going to happen is, to reproduce what you have in production, you're basically going to have to build that exact same environment in test. Down to the switches, the kind of cabling you use, the hardware cards, and a lot of time, if you're running in the cloud, your test cluster may even be in a different region, or maybe in your office as opposed to on the cloud, which means you really have to keep in mind that if you push something to test, or if you push a new feature to production, just because it works in test shouldn't give you that much confidence if it works in production. Anything in your test environment is going to be an approximation, all the way down to how clean your power is. So, but this basically means is that you're always testing if you're in production. And you should constantly try to simulate failures and brownouts, things like a box going down, or a switch going down, or somebody tripping over a cable. Some of these things can be kind of hard to automate, but you have to do it up front, or nature is going to automate your failure for you, and you won't be prepared for it when it happens. One tip I got from James Hamilton, who's one of the major architects of the Amazon cloud, is the canary in a coal mine. Write a little bit of code or change your routing protocols so that one or a few boxes, or perhaps even a whole switch, runs at 175% of the current load. So what that means is, as things cycle through the day, your users, if anything fails because it's failing at a large load, you'll see it fail in those boxes first, and you can mitigate things by closing up your bandwidth so people can send less requests to your API, or spinning up 50 more servers on EC2 so you can mitigate that load. it's really important to use your existing infrastructure to kind of test against itself as much as possible. Another really important thing when it comes to this canary in the coal mine and to understanding that there's a big difference between production and test environments is that you should write your code to be backwards compatible and deploy stuff really gradually. So, deploy to one box, leave it alone for a day and see if that's working. Then deploy something to 2 boxes and see if that's good. Then deploy it to a rack or to 20 boxes. And then you can see if anything's going to crash, and you can roll back as much as possible. Which means that, there's a great, I think it was a Velocity talk a year ago or two from, I want to say Flickr. Was it Zappos? No, it was Flickr. And that they deploy 20 or 30 times a day. And, when I was at Microsoft, that would have blown our minds because we could deploy one time every 3 to 6 months. But if you have an infrastructure where you can deploy that often, that means you can roll back really easily as well. Definitely check out some of the talks from past Velocities and from Strata this year if you want to learn more about sort of agile deployment practices. Another really powerful thing is that you should really build these architectures to fail. One thing you may have noticed, back when we were all running smaller websites or smaller applications, is that something kind of worked or it didn't. In other words, the site was up or it wasn't. People were getting their requests or they weren't. And so, but these days with these large clusters, because the code can be complex or because machines in rack A may interact with machines in rack B in weird ways, you're often going to see things like malformed requests or a machine that may spit out data every 3 minutes and then not spit anything out for 10 minutes. So if something isn't working and you've built your architecture to be fault tolerant, just shoot it instantly. Anytime something looks weird, just bring it down because you don't want your data to be corrupt or you don't want those failures to really cascade. Multi-system failure is really common as well. Failed switches, I think, happen almost as often as, failing SQL servers. So if a switch comes down, you're not going to lose 1 or 2 machines, you're going to lose 20, 40, or 60. And then if you suddenly lose a third of the capacity of your system, even if you've built this beautiful load balancing, it may load balance perfect onto the other 2/3 of the system, which will cause it to collapse from too many users. So you have to be careful. Even though your code may not depend on all the machines in your cluster, there still may be risks of cascading failures. So you'll want to test for that. And the reason why you want to shoot things as soon as they start acting weird is you really want to avoid false negatives. If something's wrong and you don't know it, because customer experience is so paramount these days, you might lose customer data. You might lose that $5,000 piece of furniture they wanted to order, or those 50 chips they wanted to order, or the new update to their credit card address. So if you've got a machine that's acting really weird, the consequences of bringing it down should be minimal compared to the consequences of it putting out wrong data. So that's sort of the first section of ops, and if there's 1 or 2 things you should take away from it, it's that you should automate your operations with your engineers as much as possible. That's the first big thing. And the second big thing I would say is that build your system to be so fault tolerant that instead of having to log into a box and fix it if something's going wrong, you can just bring that box down and come in on Friday and see what's going on, or spin up 10 new nodes in the cloud and see what's going on. So segueing from the operations to the engineer side of things, you've got to remember, and I don't mean to offend anybody here, but this is system software. This is not application software. I love my Ruby hacker amigos. I love my guys who work on LAMP stacks. But you can't expect somebody to optimize a 3-phase commit algorithm to your distributed database if they've been, building PHP for 10 years. They may be a brilliant engineer, but this is very, very different than traditional web applications design. And it is kind of hard. I learned this the hard way too. A lot of these things I've told you about so far have come mostly through me making horrific mistakes or through my friends making horrific mistakes and tell me about it. So, don't feel bad that you don't know how to do this right away. I mean, it's even hard to get Hadoop set up. So, things that you'll often see in these kind of distributed systems that you won't see in things like, like your 3-tier Ruby web app is garbage collection tuning. Do I use parallel? Do I use parallel concurrent mark sweep? Algorithms. If a node goes down, how do I determine what the best node to replace it is? What data structures? Is this a B tree on disk? Is this a LRM tree? Is it going to be mostly accessed in memory, sequentially? Things like that. None of these really have anything to do with, making sure your CSS is in order and making sure that your REST queries are well formed from your web page to your database. This is very, very different. Not to say that there's not a lot of engineers out there who aren't capable of this, but you have to recognize the fact that it can be a pretty steep learning curve. And, computer science knowledge is really required. It's not quite a luxury. A lot of times when you are, these things you mentioned above, they're covered in your computer science classes, and you don't have to have a computer science degree to build these kinds of systems, but you'll certainly have to know your basic data structures and understand how to tune your JVM and why it needs to be tuned. So, when you're looking at people to hire or you're looking at people to build these, you should really test for these computer science fundamentals. And, as much as I love DBAs and relational databases, I actually worked on SQL Server at Microsoft. Those skills really aren't useful. With these kinds of systems, DBAs have trained so much to optimize that extra 5% of performance out of Oracle database, or understanding when to use clustered indexes in in MySQL. But just because you understand how to use MySQL doesn't mean you could build a more multi-core compatible version of the InnoDB engine. Knowing how to use something and knowing how to build something can be really different. And this can lead to some friction in your organization as well, as DBAs discover that their skill set really isn't that helpful with these kinds of systems. So, another engineering practice you should keep in mind with these big systems is that you really want to minimize state in your inter-process communication. And what that means is, as you're moving data between machines, move the absolute bare minimum amount of data you need in order to sort of recreate it. So in other words, if you are, let's say you've got a site that lets you manipulate images and add funny captions in front of pictures of kittens doing things. Man, that sounds like a really good site idea. You wouldn't want to, let a user download a photo, use your thing, add a caption on top of it, and then send it back to your machine. If that picture may be 4 or 5 megabytes, it may be, moving those 4 or 5 megabytes and storing it in 10 places in your architecture isn't going to help. Instead, and I think this is what the cheeseburger guys have, is you would build a little application and they type in a text box, I can has cuddly kitten or something, and then send those 14 or 15 characters to your cluster and have your bugs. And if you've got to debug 10 or 20 megabytes of data for every one of your users, so it's really small, and sort of generated data in place are moved around the absolute minimum amount of data that you need. Another thing is that data really needs to be descriptive and not prescriptive. What that means is that data needs to be self-describing as much as possible. In a traditional SQL Server world, we're used to having files or schemas that say this table has integers in this column, strings in another column, varchars here, and so on. But if you have to, a lot of times, if you're having to pull together data from Flickr or from Twitter and your internal processing network, you're not going to have access to those schemas, or those things are going to change so quickly that what the column customer may mean something one day and another thing the next day. So these ontologies that a lot of times we determine up front and keep in documents somewhere in your wiki from hell, they're going to be kind of useless. So data should be more self-describing. With things like JSON, you can name your field customer string and it'll be typed, or amount of customers and it'll have an integer. And as you store that data, you're not going to lose that perspective you need. Whereas if you have 10 different databases with 10 different schemas and documentations on what that actually means somewhere, you're going to lose what your data means really quickly. And going along with our sort of NoSQL theme, or parts of the NoSQL theme, not everything is a table anymore. We could get away for 30 years with storing everything in relational databases or flat files because that's all you really needed. But you should really structure your data according to how it needs to be used. Are you accessing it in memory? Are you accessing data so you can figure out what other kinds of data to access? Hadoop is all about unstructured massive files that you can just crunch through. You can't access those files quickly, but you can access a lot of them. Or graphs, things like Twitter, who are friends of my friends? Friends of my friends is not something you can express in SQL, really. I mean, you can, but it's like a 6-way join, and it's all kinds of Lovecraftian horrors. Or key value stores, transaction number 428 was for $28. None of these things are really great for tables that you do joins and manipulation and OLAP against. Everything is its own data structure, which is why you need to have strong computer science knowledge if you're building large systems, because you can't rely on, databases to be your crutch anymore. But kind of the good thing is that the more your problem narrows, the easier it is to scale. So if you have a batch processing problem, but not a serving large amounts of data to people problem, then you can say, all right, this is a Hadoop problem. Let's use cascading, which I think is the best way to interact with data in Hadoop. Let's use cascading to crunch through all that data. Or we've got to serve millions of images to people. Let's put them on S3 and let Amazon handle that problem. Instead of saying, let's serve our images from our database, let's run queries from our database, let's serve passwords in our database. You can't do that anymore because your traditional database isn't going to be scalable that way. Wow. So another important thing to remember is that big data is big. Things are going to fail in really big ways. When we've got integration tests and things like that, engineers, a lot of times we run our little JUnit or NUnit test suites, and it may take 5 or 10 minutes. And then, it's over, it's done. But if you've got to process 20 terabytes of data and some pieces of that data rely on other processing steps, you're going to be in a world of pain because, and this has happened to some of our customers, it may take you a day to realize something is wrong or for your tests to give you wrong reminders. So you really have to granularize tests and test as much as possible. Another important thing is that what may work at 1.5 terabytes is going to fail at 2 terabytes or may fail at 10 megabytes. Things like Cassandra have this problem a lot where if you've got a very little amount of data in it, it's stored on one machine or it's not optimal or it's not made redundant yet. So if you lose that machine, you lose that data. There's sort of a minimum amount of data that a cluster may need to be running. Likewise, 1.5 terabytes of data may put you at 50% capacity and you'll be just fine. And then as soon as you hit 2 terabytes of data, things will start grinding to a halt because you've got a race condition where your CPU will be waiting for I/O too much. And so you really have to think about what's going to happen when I'm actually running this at scale, and constantly test not just your expected load, but expected load a month from now, expected load 6 months from now. You should have as many tests as possible, but keep your code as simple as possible. This is something most of us already know as engineers, but it's kind of worth repeating. Another thing is, when you delete data, and I know HBase does this for sure, deleting data from a disk can be really resource intensive. So instead of going in there and zeroing out that row or removing that row and then rebuilding your B tree so that this branch is now equal with this branch, you should just do a soft delete instead. Have a bit that says deleted. And when you go to retrieve that record, just have the query or something like that, things like that, just mark it as unused and the disk will scan right over it. And this is going to cause a little consternation, but you might hear the phrase, "No, I can't give you a repro very much." In other words, bugs can be really difficult to reproduce in these systems. If you've got 100 nodes and you've got a bug that comes up, when you have 50,000 simultaneous users, you're not going to be able to sort of reproduce that from home, unless you've built a pretty amazing test infrastructure. So what that means is, if you can't reproduce a bug, that means you were logging it wrong, and you need to fix your logging. Log absolutely everything. One of the good things is that since space is so cheap these days, having a 2 terabyte disk on every machine just to record every query your users make and how long those queries take, and then putting all that information to a Hadoop cluster is pretty cheap. And otherwise, you're not going to be able to attach a debugger to machine number 427 and see what happens when 50,000 people run that query at the same time. You can log everything, and part of the Spire database is built to to be able to stream logs into it easily. Cloudera has this thing called Flume, where you can, I believe it's called Flume, where you can log things into a database or log things into Hadoop and then process it with stuff like cascading. There's this new startup called Loggly. I don't know how much data they can handle, but they sort of outsource log processing. Logs are really, really important because that and monitoring are the only ways you'll ever be able to look at history of your machines and see what's going on. Another thing you really want to do is avoid impedance mismatch. What this means is that when we're working with classic databases, a lot of the times you'll be able to run a query across 50 megabytes of data. It'll be really fast. 1 gigabyte of data may be a little slower. 2 gigabytes of data may be extremely slow. But you kind of expect to be able to run queries on our database on top of anything. But these days, because you can't use these traditional databases for these queries, you're going to have problems where you have to sort of divide things. What is real time or what is batch processing? What is high throughput, high latency versus low throughput and low latency? So Hadoop is a high throughput and high latency system. You can process 100 gigabytes of data, but it may take you 100 terabytes of data, but it may take you a minute to get started. You can't use Hadoop to power web pages. You can use HBase to power web pages, but Hadoop, not good at that. Likewise, things like Memcache let you retrieve a 200 kilobyte web page and images instantly in 1 millisecond and serve it to 1,000 users. But you can't process 100 terabytes of data in Memcache. So it's really important to separate your systems according to the impedance. In general, you can think of it as you can get a lot of data eventually or a little bit of data right now. And there's also, so you can kind of think of it as, MapReduce, processing bulk data, versus indexing stuff and making it distributed. So you can do things like, I want the top 10 blogs for all author named Bob over the last 30 days. That's a very highly indexed thing. That's something our platform does. Or, sharding out full text searches. Very, very different requirements down to how much RAM you use. Sharded and index boxes may have a lot of RAM and very little disk space. Bulk processing boxes may have 2 terabytes of SATA drives. So this didn't turn out that well turning to PDF, but I'll make it easy. Here's sort of a really simple workflow that I put together at our previous company, Visible Technologies, and it's 3 very different systems. And this is something you'll see a lot if you're like a BI or an analytics company. There may be one system like Hadoop boxes, like $1,000 each with a ton of storage, and they collect data as MapReduce jobs, do semantic analysis of MapReduce jobs, and then some kind of unstructured analysis, things like how many $signs appear in this post, or is this spam? And that may be a whole cluster just dedicated to processing and collect data. Then you have another cluster dedicated to sort of serving data, storing it in HBase and doing key value retrievals and doing sort of continued structured analysis on it, generating indexes and storing those indexes in things like Hadoop. So you have another cluster, one cluster is sort of offline processing. You'll have another cluster for live processing. And then, a third cluster you may have to just keep indexes in memory for like search engines. This is what Google does. And those may have just like 64 gigabyte SSDs or 300 gigabyte SSDs and 64 gigs of RAM. And you just keep those indexes that may give you 1 or 2 kilobytes of data or pointers to a file to serve images. And that is its own kind of cluster because that's meant to serve thousands of users very quickly. So the blue cluster, this unstructured storage has 1 user and they process 40 terabytes of data in an hour. The orange cluster may have 50,000 users and can process 1 kilobyte of data in a millisecond. Extremely different hardware profiles, different code, different systems. You can't really build Swiss Army knives anymore. That kind of concludes the the engineering portion. If there were 2 things you could take away or 2 things you could take notes on it, I would definitely say that understand that this is not easy to build and that you can't really hire .NET hackers to build, a distributed fault-tolerant key value store. And also, there's no Swiss Army knives anymore. You have to understand the data structures you're using. You have to understand your use cases because you can't do things like, power your web page with Hadoop. So this sort of brings us to the third point. The sort of softer side of distributed computing is how do I build an organization that can handle these kinds of big data problems? So one of the most important things is hiring folks. You need to plan for more engineers and less ops because ops isn't going to scale if they can't write code. If you've got 2,000 machines and you used to have 1 person maintaining 2 machines, you can't hire, well, Microsoft does this, but you can't hire 1,000 folks to run 1,000 machines, especially if you're a little 5-person startup. But it's not that hard to hire like a really rock star engineer, and these guys are not cheap. Good engineers, especially if you're down in Silicon Valley, are going to cost you $150,000, $200,000 a year. But they'll save you $10 million in hardware and $10 million of hiring ops guys. And so, the ops code guys are very good about theirs. They're the ones who write Chef. And you should plan to hire lots of engineers and don't hire that many ops guys because as much as engineering will grumble, it's their job to fix those 2 a.m. phone calls because the bug is probably in their code. This is something I saw in my last company. There's kind of a context switch cost when training relational database guys. If you need a relational database person to switch from using something that's not super scalable like Vertica to running, like helping administer some crazy scalable key value store, none of their skill set's going to be useful besides maybe monitoring to see if the cluster is up and down. Or if you're an analyst and you have to do something like having them write SQL code on Hadoop, there's things out there like Hive, but Hive, which is kind of SQL on Hadoop, but that doesn't mean that you can do real-time queries on Hadoop, or that those queries are even going to look like classic SQL. I've seen some Hive code where like you have to manually partition data across multiple machines. In a classic MySQL box, you don't have to do that, so you don't know how to do that. As much as you try, you can't really abstract 100% of the pain of working MapReduce away. Sometimes you can get close, but these relational database world, even if you're doing things like MongoDB, MongoDB is a kind of interesting single document store, although it too has its scalability problems. But it can do some pretty impressive stuff. You're not writing SQL queries against that. You're writing JavaScript. And so you don't want to hire DBAs and you don't want to hire ops. You want to hire more engineers. And you can also kind of run into what I call the infinite resource hell. And this is something Pat was telling me about, I think at Pat Helland, one of the big researchers at Microsoft, was that as groups get more access to more data, they lose visibility on the limitations. So if you've got 5 different groups and these guys suddenly realize, hey, I can run queries across 500 terabytes of data and it's totally scalable. And it may work fine when only one group is accessing that cluster, but then as more and more people learn these tools to access this data, you're going to see problems like, more and more jobs are taking more time, and you're going to kind of lose visibility because one organization isn't responsible for all their data anymore. Things that used to be siloed. This is our transaction database. This is our data warehouse. This is the results from our marketing campaign. This is all going to be in one giant Hadoop cluster now. And orgs across the entire company are going to want to try to run jobs against it. Which means that you really have to manage resources and things like data visibility higher up. What may have been a problem simply because, marketing didn't have access, the username and login to the transaction database anymore, now has to be monitored at like the VP of security level or CIO level, because you have to delegate these resources to these groups, and folks need to share these resources on a much larger scale. And so the responsibility of managing all this kind of goes a lot higher up the chain, and that can be a very, very difficult thing for enterprises to sort of get a hold of. And this is a really new and evolving field. What may be hot 6 months ago is not hot anymore. So, MongoDB, you may have acquired all the skills you need to like roll out an awesome MongoDB cluster 6 months ago. I think Gilt ran into this problem. And then as soon as you hit a certain scale, or if you change your business model, I think Gilt switched to Voldemort for a key value store because MongoDB couldn't handle those amount of transactions they had. So which means the entire organization from the C level, they're not that big, but maybe 20 or 30 people from the C level down to the individual engineers had to learn this new stack because they're working at scale. So things are going to change really quickly. And a lot of this isn't just coding anymore. When you build these systems, you'll probably spend 50% or 80% of your time just trying out iterations, what systems work, what systems don't. And that can be really, really difficult to articulate to management that there's going to be no new features for 6 months because you have to build a whole new database from scratch. You're going to spend a lot of time experimenting, and this can be kind of hard in some people's careers because it's hard to deliver something people can play with and click, which makes it really hard to do with Scrum and Agile backgrounds as well. And coding all this stuff from scratch is really, really painful. But it's painful to nail together 10 open source projects as well. Processing stuff with Hadoop, full text search with Elasticsearch, dumping it into MySQL so you can do some real-time OLAP, building dashboards out, with Ruby on Rails, serializing it all with protobufs or Avro. And none of these things is really meant to work with each other. It's one of the reasons why we built Spire, for example, is because we noticed that you have to nail together 10 or 20 open source projects to have an end-to-end real-time data platform. So doing it yourself is really pain, and you have to make people understand that you're not building websites anymore, you're building infrastructure. And you should open source anything that's not your secret sauce. Anything that's not the algorithms that run your business or your customers or your user interfaces, but open source your improvements to Rails to make make it more scalable, or open source your improvements to Hadoop so that it doesn't lose data in certain kinds of crashes. You really have to get as much stuff out of your organization and well documented as possible, because you can't possibly handle it all. This kind of leads us to an anecdote Jeff Bezos said about why Amazon, why the Amazon cloud is important. And the story basically goes that he goes to a monastery out in Bavaria, and he sees that these guys have their own generator to power their water, or to power their water power their water filtration, and to power their machinery. And they're really proud of it because they're so independent and they are so into the German purity laws that they even have their own electricity. But you can't taste the electricity in your beer. Nobody's going to know if it comes from the Hoover Dam or if it comes from a generator in your backyard. Outsource as much of your infrastructure to the cloud as possible, or automate as much as code as possible. Don't have the nerd pride that I see so much here in Silicon Valley, where you want to build everything yourself, because something that solves 90% of your problems is going to have a 10 or 100x impact on saving you time and money. And this is something we talk about a lot with our customers drawn to scale, and that you should look at a lot when you're rolling out things like Hadoop, is be willing to sacrifice that 100% absolutely perfect problem solving for keeping it fast and simple. End-to-end platforms are good. So I guess to summarize, and we'll move on to our Q&A portion now, plan for everything to fail, and you have to test it and yank the questions and so on. Plan for yank the boxes and so on. Plan for everything to fail, because you don't know when or how bad it's going to be. And if there's anything to take away from this presentation, to take on notes and to put on a whiteboard, this is it. Test constantly in production, because your test environment is going to look nothing like your production environment, and you want to know what's going to happen when your customers actually see these problems. System software requires computer science. This is not writing a 3-tier web app. This is very difficult problems you have to solve. Even if you're using things like Hadoop and HBase, these are not point-and-click things. You have to roll this out, configure it from scratch. And don't build it if you don't have to. Don't get rid of that nerd pride. And just use what's out there. It's almost always easier to tweak something that exists for your problems than to build it from nothing. So cool, thanks. We're going to do Q&A now. To everybody who helped me with this, there's a list. Follow these people on Twitter, Google their names. They're all really popular folks, very wise. They know a lot more about this than me. I've only been doing this for a few years. Most of these folks have been doing this for 20 years. And thanks to everybody at O'Reilly for inviting me out. You guys are awesome, and you are a vast fountain of knowledge. And useful resources. 3 big blogs about scalability are mine, Road to Failure, highscalability.com, and James Hamilton's blog there. And feel free to check out our Spire database. And definitely fill your name out on the forums and we'll contact you. Our database handles everything from structured queries to full text search with large amounts of users very quickly. So let's go to some Q&A now. So Saptac wants to know how to automate deploying a 500 node Hadoop cluster from bare metal. Great question, because nobody has. The closest thing I think out there is Chef, and Chef has these recipes that will allow you to maintain and roll out 500 Hadoop nodes, and the recipe is called Hadoop for Chef. Cloudera, if you're using Cloudera distribution, they say they've been working on easy deployment, but I haven't seen any tools for it yet. There's a lot of competition coming up in the Hadoop deployment space soon, so keep your eye on it. But for right now, shell scripts or Chef are your best bets for large Hadoop clusters. And I think Chris Wenzel might be in the chat room here, and he knows a lot about automating Hadoop as well. So Steve asks, what are job titles for these engineers? Systems architect? That's a really loaded question. Out in Seattle, systems architects mean, things like, systems architects mean, database guys. But I think if you call this title distributed systems architect, or platform architect, or distributed platform architect, or scalable systems architect, something to set it across, that's a good way to start. But a lot of these folks, we work at organizations where we don't really have job titles, or we may just be engineers. And you just may be an engineer at Google and you happen to design Bigtable. But that title isn't going to show up on a resume. Hiring these people is often done not through searching job sites, but through personal connections. So Steve also asks, how do you keep data secured on these scale systems, especially if you're in the cloud? Security is not really my thing. I don't really even know how to begin to answer that question. I mean, things like Hadoop have very basic sort of tables that let you figure out who has access to what files. Let's see, good people to follow on Twitter are at Beaker. He knows a lot about security in the cloud. And I think who else? At James Waters, at Randy Bias. All those folks, and if you follow me on Twitter, I'll probably retweet them. They know a lot more security than I do. Darm asks, I am building a semantic search engine and it is demanding 480 gigabytes of RAM or 12 days to index 2 million queries. How can I scale it with a budget of $100 a month? You should probably find a new search engine. I need a lot more information to answer that. But, that's $100 a month doesn't really help us here. But you might want to think about, why is it demanding 480 gigs of RAM? Do you have to serve it all from memory? Why does it take 12 days to index 2 million queries? Is it some sort of graph where you have to traverse the whole thing? I mean, look at your data size. It sounds like you've got some scalability issues there and need to go all the way down back to your algorithms. So commenting on specific databases for scaling. This should be really fun. You can check out my blog, roadtofailure.com. So this is Michael Ritchie wants me to comment on specific databases for scaling, such as MongoDB. A good guy to follow on Twitter about this, besides me, I'm Luscious Pear, is Tim Anglade, Timanglade. And so there's kind of three categories of databases that scale in different ways. There's a traditional relational database, which doesn't really scale in any direction except for up, meaning more hardware to go faster. And you can make a traditional database distributed by keeping machines on separate boxes, and so on. And then you have to write special queries and things like that. MongoDB and CouchDB are really great for the use cases, of storing documents. They're not very good for things like OLAP or for manipulating data, generating complex dashboards, but they are really good for document storage and retrieval. There's probably a bit of an issue of contention with this, but I don't really think CouchDB and MongoDB are built to be as scalable as you would think. CouchDB probably has been distributed longer, but MongoDB's scalability systems where dividing data across multiple machines is still very new and has a lot of problems. Ultimately, the problem with things like MongoDB and CouchDB is that your data may be distributed, but your indexes aren't. And this is a really, really painful thing, because if you want to do queries like top 100 blogs by author name, where author name starts with the letter A, over the past 20 days, or I want all tweets from these 20 users. With things like MongoDB and CouchDB, if you need to run those kinds of complex OLAP queries, you have to run that query on every single machine. And this is like a whole other topic, but you have to run that query on all 50 of those nodes because the index isn't distributed itself. Our database, Spire, does have distributed indexes. So, with our stuff, you lose a little bit of functionality, but you gain a lot more in terms of scalability. And being able to access data very quickly, because if you have a truly distributed index and you need to access all blogs by author name Bob, that's a query to one machine instead of 50. So that was a little long. And then sort of the third category is sort of key value or tabular stores, things like Cassandra and HBase, where they are totally scalable, totally seamless, but they don't have very much functionality. You can store things by primary key, retrieve it by primary key. There's no query language, and it's really hard. And besides that, you have to scan across hundreds of terabytes of data to get the values you need. HBase is what I trust the most and what I use the most, and it's really great for, StumbleUpon uses it. Facebook has a 1 petabyte cluster of HBase to power their new messaging system, but you're not going to be able to do like OLAP-y slice and dice queries with it. Please send me an email, if you want to learn more about that stuff. So Rohan asks, what are the tools for log monitoring? And that's another field where there's a lot of opportunities. There's things like Loggly, who are sort of log monitoring as a service, but I don't know how much data they can handle. There's some really old stuff out there like Splunk, which handles log visualization and monitoring, but Splunk isn't a very distributed architecture. So you can really only have a few nodes of logs. There's a lot of things like, Flume, to put log information inside a Hadoop database seems to be very common. Or putting your logs in Amazon S3 and then processing them with Amazon MapReduce to sort of get bulk information out of that. Amazon Elastic MapReduce is Hadoop as a service. Really cool stuff. And then there's things like our database, where you can load your logs into it and index the logs and then manipulate it in real time to generate cool charts and graphs and stuff like that. Logs is a very unsolved problem, but a lot of folks right now tend to dump files to S3 and then process it with Elastic MapReduce. Guy with Dogs asks, if we don't have the skills for this in our organization, what do we need to ask in interviews to truly vet a candidate who really does have the needed skill or imagination? That's a really good question, because a lot of organizations have big data problems who didn't formerly. If there is two things you could do to understand scalability problems a little bit, it would be to read the Google file system paper and read the big table paper. If you can understand a MapReduce algorithm, then that might be a good start towards understanding distributed systems. I've only been doing this for 2 or 3 years, and I've gotten to the point where I was able to start a database company. So anybody with a good computer science background can use it. So really emphasize computer science questions in interviews, or better yet, look at work they've done already. See what they've done on GitHub. Ask previous employees. people to build these kind of systems are going to be very difficult to hire. But if you have people with great computer science backgrounds who are willing to read the papers and hack, you're going to be all right. May take you a while, but you'll be all right. Akbar asks, Bradford, do you have any thoughts on the future of big data and personalized medicine and bioinformatics? This is something you should really come to the Strata conference to learn, because there's going to be a lot of bioinformatics stuff there. I mean, big data is exploding, especially in that field. But it's kind of funny because genetics is not a big data problem. I think the gene for an average human is, a few megabytes at most. But protein analysis, metabolics, things like that. There's this company I know up in Seattle, Systems Biology, who generates something like 100 terabytes of metabolics analysis information a day. And Hadoop can barely handle that. There is so many unsolved problems with big data in biotech. And it's booming like crazy. You should totally come to Spire, to Strata, to learn more about it. Chaim asks, is Spire open source? We're not open source. We use some parts of Hadoop and HBase, but definitely go to the Drawn to Scale website. It's a little sparse right now, but drop me a line. I'll be happy to tell you more about it. And Guy with Dogs really asked the perfect question to wrap this up. If my client wants to use SQL Server, Oracle, or MySQL, should I find a new client or charge by the hour? Charge by the hour. You should always charge by the hour when you're consulting, in my opinion. It really depends on what you want to do. Using traditional SQL means if you want to do anything more than retrieving or storing very simple data, like if you want to do OLAP or something like that, and you have more than even a few terabytes of data is going to be horrific, it's just not going to work, period. Maybe if you get enough, if you are a Twitter and you hire 10 or 15 of the best distributed systems engineers on the planet to build amazing stuff on top of MySQL, you can kind of make it do whatever you want, because at that point it's just a glorified storage engine. But you're not going to have benefits of SQL. You're not going to be able to do queries because your indexes aren't going to be distributed. And you're going to have to write, all this stuff to determine if a server is down, bring it back up, how to rebalance data across servers. It's a total non-starter. And if you really want to learn the horrors of that, follow Ryan Rawson, who's one of the architects of HBase. I'll put his Twitter handle in chat. It's at RyanOBJC. And he can articulate really well some of the pains of making MySQL distributed. And there's some presentations on SlideShare about using HBase at StumbleUpon and Streamy. It's pretty old, but it really goes into why you just can't make MySQL distributed without a lot of money or sacrificing a lot of functionality. It's 11:15, so I guess it's time to go. Thanks a lot, everybody. It was really fun. Those are some really great questions. Follow my blog, Road to Failure. Follow me on Twitter. Drop us a line at Drawn to Scale if you're interested in our easy-to-use distributed database. And just, if there's anything to take away from this, it's remember that this is computer science. Hire developers who can write operations code and really solve the essential problems, because there's no Swiss Army knife anymore. Build systems that solve the bare minimum problems you need to get to production and solve and make your organization money. Thanks a lot, everybody. Have a great day.
Thanks, Bradford. I just want to thank you and thank everyone else for joining us here today. Let's see, you guys can hear me, right? Okay, great talk today, and I thought we had an awesome crowd too, so we had some really good questions. And I just, once again, I want to thank our sponsor, Thomson Reuters, for making this possible. And I will get the recording out to all of you in a few days. We'll send the link out to everyone who registered for it. And if you didn't register, just check our webcast page, O'Reilly.com/webcast. once again, we want to remind you to check out the Strata Conference coming up very shortly, and you can find that we have a discount code that will give you 25% off, and I think, Marcy, can you or Gretchen post that in the chat room? And that's about it. So thanks, guys. Hope you'll join us again next time. Bye.